Yeah, welcome everyone to lecture 5 of our Cloud Computing and Big Data course today. The topic of this lecture is MapReduce, which is today really a computing paradigm, but we will also observe that this is not really new. We have talked about this any now and then from these lectures, but the principles of MapReduce go back to a computer science technique called divide and conquer. So it's a quite interesting lecture. And brings us also back to a more, let's say, practical lecture, which is split in 2 parts. So we would have a more conceptual lecture today, and I will bring a practical lecture 5.1 in the next course hours, then probably on Tuesday, where we then have some running examples in the cloud. We're really using MapReduce. But before we dive into the material of lecture 5, let us just review a little bit about the conceptual aspects we had the last time when we talked about data center design, which is largely fueled by virtualization. And we said, like, normally nothing really changes from the way how you operate a computer for the user in a way, right? You would see on the left-hand side, on the top left here, the traditional computer still looks the same. We would have hardware like a disk, the CPU, memory, etc. And you have some form of application, you're just using that. What virtualization now enabled was, and basically with this virtualization layer in between, is that you a little bit encapsulate and abstract from the real physical hardware to a sort of virtual hardware. You see that basically directly beside when you have after virtualization. And by doing so, you have much more flexibility of doing different things. Some of you know very well if you, for instance, have Linux and Windows, right, as an operating system. And you need both. I mean, people in work require you to do PowerPoint, others want you to do Linux because it's better for coding, it's better for programming, maybe also for administrations of systems. But in a way, you need both. And what would be a solution? You create, a virtual machine. And with a virtual machine, then you can run a guest OS, as we discussed, which is then either Linux or Windows. And there were different models if you dive back to the lecture 4, but this is of course also not the core of this course. The idea of this course is now to think big. So big data, what happens if you scale up? What happens, and how actually is virtualization playing in the game when we use a large virtual cluster running Apache Spark, for instance, what we have done in MS Azure. So this is something where it brings us then to the right-hand side on this, where, the red seam is really standing for bringing it in a very big setup. It's not anymore thinking about your little computer or laptop. You have a real data center that you see there in the picture. Maybe a Google data center, a Facebook data center, even our systems at the Jülich Supercomputing Center in Germany are similar here and there. So this is, of course, something to think about, that virtualization has enabled this cloud computing. And this is a takeaway message. You could say that basically without virtualization, these cloud movements would have been not really possible. And on top of it, from thinking about the possibility, also adding the idea of making it feasible in terms of money, because the scalability, of course, costs a lot of money. Some of you explored this in the assignment, letting the Spark cluster running. So this scalability costs. And if you see the graph below, if you would have to do this in physical servers instead of logical ones, which would be then maybe idle every now and then, you would have a lot of things to do instead of using the virtualization, which actually has a better resource utilization. And with this resource utilization, and then really think big, right? Like these Google data centers, they're many-fold football, soccer fields. They're huge in size. If you have these size, then this so-called factor economics of scale come into the equation. It's much more better essentially to say, in this context, the bigger the data center, the better the costs, right? We learned already there's lots of hardware errors and failures on the way, and actually we will address this today in lecture 5 a little bit also, how we deal with this on the software level. But still, it's economically much better to go the economics of scale way than operating extremely small data centers. And this has to do with many different factors, not only the hardware, also the personnel, the humans that really have to repair aspects of it or maintain aspects of it. It has to do with the infrastructure that you also nicely see in the Google example, where there are a couple of pipelines. So cooling plays into the game. Is it liquid cooling? The air ventilation, you have seen the diesel generators. In a sense, the whole building has also factors in it, especially when you think again on the aspects of the footprint of these, which partly around the shilling, for instance, it takes 1/3 of the whole costs of a data center, right? Just cooling it down. So talking about all of this means virtualization is really an enabler of different applications. You see this on the top right. You use a physical cluster with different virtual clusters, so to speak, across different virtual physical clusters. You have a very flexible setup, and the whole goal is to achieve mostly 99% utilization. Usually you don't, or you never see 100%. Basically because it's a scheduling problem of always, fitting the right sizes. You see there virtual cluster 2 on the top right has some, let's say, free space on the left, but it's just nothing fitting maybe inside. So there are challenges, of course, to have a resource utilization which is always 100%. But today, depending on the scheduler software and also on the load that you allow, right, on these systems, you can achieve even 100% if you do smart scheduling and also, let's say, very good policies of just don't allow too small jobs, or to some certain extent do interesting backfilling scheduling mechanisms. But these are all topics we address actually in the HPC course much more. And as a cloud computing course is much more on the higher level, thinking about how we deal with the cloud. We come to the idea on the bottom left that you see there, which is largely everywhere in clouds today, which is about resource sharing. And this means we have public clouds, you have private clouds, hybrid clouds we discussed, depending on how many people can access it. But the key idea is really having a flexible resource sharing available through the internet, so to speak, really remotely. So the idea is, of course, not that you create a cloud data center directly in your company, except, and that's what we discussed at the end of lecture 4 last time, you have a private cloud with very sensitive data, for instance. So then it makes sense maybe to have a private cloud, and for some calculations, like aspects of federated machine learning, you would then use partly the public cloud to do the computation. But these are all more, let's say, advanced topics. Coming back to the cloud itself, again, virtualization is everywhere. And you see lots of benefits in the lecture 4 that we discussed. One of it is, of course, a live migration, which is interesting, especially if you have failures in a system. And this is also something I want to come back today when we talk about MapReduce, why it was actually created, why there was a drive to go, let's say, away from programming models we teach in HPC with message passing interface, OpenMP for shared memory programming, why there were different factors essentially, and one of these factors was differently dealing with failures and so forth. So let's come to basically today we said it's a green course, which means it's much more practical topic. Again, admittedly, lecture 4 was a little bit of theory behind it, but of course it has practical implications. But now with lecture 5, we will split it, as I said earlier, in 5 as a conceptual idea and theoretical view on MapReduce and Hadoop and so forth. And the next lecture will be then really a practical lecture where I go and show you some examples of MapReduce in the cloud. And of course, this would be a little bit related to your assignment 2 that is already coming up. Hence, we put this also earlier in the course than we had it in the beginning when we started this course. So also this is based on student feedback. And we'll, let's say, cover conceptual aspects like online social networking, which we also actually tackled a little bit today, and other aspects like OpenStack then in the later part of the courses. Hence, we are already diving into the material that is relevant for assignment 2 without having completed assignment 1 yet, but just to give you the chance for assignment 2 to come very early. And the outline of today is really understanding MapReduce. As I said, it's actually not so difficult to understand. And the key reason is because it is rooted in a very normal principle that we apply in human life. divide and conquer, right? You break a big problem up into smaller problems and solve them separately. That's how we basically use in problem solving skills anytime every human does this in a way. So in a way, it's really good to understand. A little bit more tricky is to understand why we need that and why it was so successful. It was derived from Google addressing certain problems that were existing. And I talked about increasing the reliability of software. So lots of remote and distributed and parallel computing software was always failing because the hardware underneath was failing. And which is just naturally if you have large data centers. And then another aspect of it is when you have, experts in biology, if you have experts in quantum chemistry, they want to do computing, whatever they do, these scientists and engineers, also for construction business maybe, they don't want to know the deep down details of a parallel system or cluster. Still, they have CFD, computational fluid dynamics simulations or something, which are very complex. So here was, of course, then something created which should hide all of this complexity, and we'll talk about it. Now, when we look deeper, though, in MapReduce after that, we will see actually this two-phase paradigm are actually three phases, and I will make the case for it. If you look in the literature, you see often a two-phase MapReduce, and the third phase is essentially added by really understanding the key value data structures that are in Apache Hadoop and MapReduce implementations, where the framework does also something for you in order to better understand and then, of course, have the benefits of this MapReduce. We also talk a little bit about a Facebook application. That's also perhaps a very interesting application example for you, showing that Facebook has not one big solution. It has actually hell a lot of different solutions for different purposes. And we will talk throughout this lecture courses here in the next couple of weeks about this again and again, how different software is applied to different problems. Then in the second part, following the first part here, we will talk more about the larger picture. If you think about that, MapReduce is now, let's say, one key brick in a big Lego house, if you want. You could see that there's a big ecosystem in cloud that built around MapReduce, not only about the computational aspects of it in mapping and then reducing tasks, rather than the Hadoop distributed file system that is actually everywhere in these different so-called Apache stacks or big data analytics stacks, as they're sometimes called. So we will talk a bit how that is actually realized with the replication concept. And of course, with this, we'll give some lights on the benefits for cloud, especially for big data applications and context. There are here and there some application examples I want to put out for you already, but of course we will have this in a practical lecture 5.1 much more when we talk about it. And this is a topic that touches several interesting challenges, because if you have now a software that you want to deploy in a large data center, you would say failures is one thing, I have to deal with it, but what about the configuration? What about a deployment? What about the scalability of this deployment? And do I really want to sit on all of these different nodes and install it myself manually? No. So there must be tools which are semi-automated, I call it sometimes. Of course, they claim it's automated. In a way, you would say it's a bit semi-automated. You still have to, have configuration files to fill in and prepare this. But the good news is you can really scale a cluster today very easily with these tools like Kubernetes. There are Docker images available. And with this, the scalable deployment that you have in clouds to think big, to be ready for big data, is really much more simpler than, like 15 years ago. And this is all part of the MapReduce ecosystem, but we cannot fit this all into this lecture today. That's why we also will address it, of course, and will link to subsequent lectures, also at the end of the course here and there, but also in between. An interesting aspect is if you want to create your own cloud, for instance, in-house private cloud, as we discussed, for some sensitive data set. There we basically talk a little bit about it, that OpenStack is also supporting this quite interestingly enough, also specifically for Hadoop, for MapReduce, for these kind of applications. And then we also talk about some limits about MapReduce. As a university course, we should not only look on the positive sides of it, we also to have a look on the negative sides. And with this, we fulfill lots of promises that we had from lecture 1 on over to lecture 3 of really better understanding what HDFS is, and basically we'll go today and understand it. So fasten your seatbelt, we go and understand first the MapReduce approach before we come to the HDFS and the file system aspects. In one of the earlier lectures we had actually the big data analytics already discussed. I just want to say it again. Here is a sort of distinction which stand the test of time. The data analysis usually stands for causality. So every time I talk about big data analytics, it's much more about machine learning in the terms of correlation, not really physical laws that really determine causality and things like that. So here we really think about the data speaks for itself somehow. We look in patterns, and the big data analytics has lots of computing power, so enabling infrastructure that goes along it, right? We don't do scikit-learn on our laptops anymore. We do large Apache Spark runs with Python Spark and the machine learning library, for instance, on a whole cluster. So this is much more the big data analytics term. That is just for a review, and let us have a motivating example about machine learning and data mining applications. Here, the interesting properties of all of these are actually to think about nice parallel. And this is actually a difference to the HPC world, where you have a massively parallel paradigm where things are really much more interconnected to each other. If you want to have the weather here on this sailor on the right-hand side, he swims in data, but he has basically the problem that one wave propagates to another wave. It's something what we do in an assignment in the HPC course, right? We will do exactly this, waves and propagation through different parallel entities. There, one node affects the other directly, right? You cannot just wait for a longer time, which we call nicely parallel. So nicely parallel rather means independent. So you could do lots of independent things like counting words, which we actually will explore later, or that you see here. You can basically see the different links on all the different websites, where they link to, where they're coming from, and so forth. And then perform essentially an iterated matrix vector multiplication in a nicely parallel fashion. And the same is true actually for the billions of edges in graph databases. These are problems which means there is a lot of data, but in a way it's regular. The links that you see here, for instance, performing ranking of web pages is a very regular structure, and you can independently process this using, for instance, as we discussed already in one of our previous lecture, our Scalable Spark example. And we will talk about these data analytics techniques in lecture 11 much more than today. So I leave it to this and shed more light what MapReduce really is by thinking about why we're creating it. So I talked again, basically in the previous slide, about the specialized parallel computers for, weather, climate research, the guy on the boat who wants to know its wave heights in the next hour. So these are things where you need a parallel supercomputer, very interconnected. One wave in 1 second is actually directly affecting the next second of this guy on the boat. So there is something which you hardly can do nicely or independent. You could also say the waves left to me doesn't matter to me, but in an ocean, if you are there, it matters to you. So that's important. If you think now large clusters that dominate by far the data intensive computing field we talk about in this course, means it's a kind of cheaper parallelism. It's not a really interconnect needed. There are lots of problems that you can do nicely parallel independently, and then later on merge the results and report it. We will have some examples later on. And so still we need basically a data processing machinery, right, to perform this big data analytics. And we see, of course, today that more and more these systems get somehow intertwined. That's basically cutting edge research, where you find also selected smaller HPC systems now in clouds. You will find several architectures that alongside HPC put a kind of normal commodity cluster for different aspects of your workflow. But still, these kind of paradigms remain. And this is really something what we already had in one of the previous lectures, which stand the test of time and will be always like this. We have high performance computing resources where the most expensive part of it is really in the interconnections. And then we have high throughput computing where it's just about how much data you get through, right? Some call it even farming, right? So growing and using on the farm, putting it all to different, let's say, fields and put your jobs out. And then at the end, you kind of collect what you have had grown. So these are different ways to describe all the same thing. That's why we talk about these two here about computing paradigms. So the motivation then for this was because HPC was existing a long time to make it more simpler. So people and of course the vendors primarily have started to have an unbelievable complexity of these systems. So concurrency and computation was of course another added value, right? You program in parallel. So you have concurrent processes. And if you have to do it on yourself, and if you want, you can do this in the HPC course, then actually you really experience that it's not as trivial as just programming a little bit of Java or a Python, let's say, script, right? You have concurrency, you have to think about message exchanges. There's another paradigm looking into the memory. You have to see that you have the right things in the memory and threads. Anyway, it all doesn't matter. The point is it's getting really complex to work with these. And you have different heterogeneous architectures, which actually change very quickly in the HPC domain and in the parallel computing and distributed computing domain. So with this, you start mapping your problem differently that you see on the right-hand side with domain decompositions in blocks, cyclic, whatever. And all of this contributed to what you see on the slides, to really burdens on the programmers and the users. And the idea was then, and that's why Google created it, to really have, this kind of KISS principle, keep it simple and stupid. Of course, not too simple. We're still talking about distributed computing. We're still talking about having lots of computing power with storage and data, but it should also scale and then handle problems and failures, as we discussed as well. So we see in a way, of course, we come back to a little bit of complexity. Still, the idea is to hide it from the users as best as you can, right? And you see here, for instance, a medical doctor who is analyzing a very tough, patient data collection. And then those people don't want to dive deep in technology detail when they are sitting in the lab. They are not the experts for that. So it's something to say on one click in the cloud, I want to have a data processing machinery that does a little bit of machine learning, a little bit of statistics, come back to me, and then it should basically give the results. I don't want to know the deep down details. If it's a Spark cluster, if it's a Hadoop, if it's a HBase connected to HDFS, I don't want to know these details. And for this is cloud, of course, just the perfect thing to do. You don't care about scheduling in a way. You don't care about task distribution, synchronization, and so forth. And so all of this was kind of a driver to really have a new technology. And then you see the people here on the time, you see that data is accumulated in all of this. Google has experienced this firsthand. You remember that Google was better at some point in time, right? I know this time very well. I used Google better a lot. So funny enough, now Google is very strong, but they had one thing they always thought about, and this is what you see here: scalability, grow up, go better. So not one user is using the search engine, but suddenly a million, then billion. So the scalability inherent in the process was, of course, something which was also very key and instrumental to the idea that you see also later incorporated in the worker ideas. So essentially, going back to the previous lectures, I don't want to spend too much time about as reason for failures. We discussed it already in lecture 4 a lot. Hardware always fails. And of course, somehow the machine should go on. You see here a lot of, you have 56 accelerated compute nodes here as an example in jewels. You have 4 times NVIDIA V100 GPUs at each of these different compute nodes. And of course, then lots of storage related to it. This could always fail, right? And so we have to learn that we have to continue to operate such big systems. And that is exactly where also then the second, let's say, motivation for MapReduce, not only make it simple, also increase the reliability. And then a sort of other motivation came just from Google, but many other players. Facebook was starting, other online social networks starting. YouTube actually started. So more and more data got accumulated in the data silos. You see that here, right? It's getting bigger and bigger. And when you have a couple of gigabytes, you don't think about this. But when you have terabytes and then growing petabytes, as we observe today, and actually we are in the research, we already are in the exascale domain, so even one more further, you would see that you don't want to transfer this data anymore. So you need a principle that later on is actually named as a data locality principle in this big data analytics work that really had the power to say we want to have rather cheap computing alongside the data somewhere in so-called data nodes than shifting for a lot of time this petabytes to a large data center and not just to be computed. Of course, this means you have to already accumulate the data in these data centers, right? Which is now, of course, for these data centers also a good idea how to keep customers, especially because you charge, of course, for any transfer in and out the data cloud. Things we will also explore in different other cloud lectures we have later. So this brought basically a big movement into the game called the big data analytics frameworks, which are very simple in a way, reliable, but hide in a way lots of the complexity. By doing so, they abstract every now and then and have, let's say, the negative connotation of being sometimes very slow. But if you want to have cutting edge performance, then you go to HPC, then you program MPI, and we have even experts in Jülich, for instance, that program assembler, right? Just to be as fast as possible. So if you want to do this, then this is not your domain here. This is really something of thinking it should be simple. It should have lots of data. I want to have simple tasks going through it. And in order to achieve, let's say, some specific problem. And we've touched already on it, thinking about Apache Spark and how it's different from Hadoop. And Hadoop is essentially more on the file system area, really having the power of a distributed file system, which Spark actually also uses. It needs a file system, but it, of course, has many aspects more in the memory, as we discussed in one of the previous lectures. So how that works, the origins, it was really a kind of beta technology from Google. I remember that very well. We wanted to have, at that time, a parallel implementation, which was closed source. And only very later, Google actually then in 2006 and 2007 came up with the idea of opening up these sources, and basically then the Hadoop movement began, really an open source community, which is extremely lively until today. We saw different versions of Apache Hadoop, 1, 2, 3, and more around scheduling, really learning from the HPC community how to do scheduling. The initial versions of Hadoop didn't have really a proper yarn scheduler that we discussed in our previous lectures. So lots of added business. And of course, having this, we will also talk in lecture 5.1 a little bit more about some really application examples in modern clouds today. Here we really focus a little bit on the idea, and you see already you have this map task. That's where MapReduce comes from. And you have this reduce tasks, where you basically have then from the divide and conquer now the conquer strategy of achieving some form of a combined output. Key to the success of this is to have a good data structure, which is a key value pairs that you see here. And the grouping by keys is something which is not, let's say, in a very task which is not important. So we will see that in the subsequent slides. But if you want to go back, here's a paper in 2004 where really Google describes all the details that we will also cover in our lecture. So again, for some of you who are maybe not so deep down in computer science, let us review shortly divide and conquer. As I said, really much human strategy these days. You basically have a problem, you have different worker nodes to do this, you distribute it, you have different processes, so to speak, handling this. You would, for instance, have all the ratings of all movies, and you want to work on the computing side to have the similarity of users and analyze those ratings. You essentially can do this in a very parallel way. And at the end, you want to combine it for giving recommendations for a particular user. So this is an example of a machine learning problem, data analytics, also what we will do a little bit in lecture 11. But it's always a strategy, partition the problem and then combine the results. And so you see, it's not completely new. MapReduce follows the same strategy. It is essentially mapping all basically to this partitioning process, what you have in terms of data, to this worker nodes, and then basically do something, and then they come up with some results. And then, of course, you want to group then these outcomes. You want to basically then in this reduced task do different elements. And it's best explained, of course, if you have some examples. So we go with a couple of examples later. But before we go there, please always have in mind that although we talk about MapReduce as a two-phase, it is a three-phase, right? And you see this very nicely by the group idea, that basically the grouping does some active aspect on the key value pairs that you provide. There's not just something dropped in terms of data. There's a smart technology that actually can not only group, it can sort, it can shuffle the data, which has been used in different algorithms. So it's a really important part. And the key aspect of it is, if you define the key value pairs very well, you can say it's automated and done by the framework. And of course, by all of this, it will handle the we'll basically then use let me just think about here. I think here we don't need the kind of music for it. But again, coming back to this, we basically see that this key value pairs, of course, are loaded and needs to be properly defined. You basically have an idea that you have one type of key that you list to a, let's say, a new key entry that is then sorted, group, or shuffled, that you then on subsequent runs can then reduce. So you have seen this basically in the example of the sandwich, which was of course a very interesting example. I can also play it again from the beginning. You have seen here basically different types of the sandwiches, which have, of course, different ingredients. You want to carve out the different ingredients, so you map that in this first step, and you have a JSON file. And then basically in the reduce step, you don't care about each individual sandwich anymore. You think about the bigger picture. You want to combine how many bread I need to buy, how many ham, how many salami, etc. I want to buy. Of course, this is a really playing example. So let's go further of thinking like the, let's say, Hello World example in the world of MapReduce, which is also very simple to understand. You would have a Twitter string stream that comes in. You would have different documents. You want to see how much sports terms are inside, how many political terms are inside to categorize them maybe later. You want to count words in all of different texts. So you would have this as a map where you just basically always in each of occurrence of the word put a +1. You say, okay, it's so many times inside if you have a word vector, for instance. And then later on, you reduce about all this. Different documents, for instance. And of course, the documents you can scale out. You can put this all over the cluster. It's not dependent on each other. Each document can do, this separately. And if you do this in the way on the left-hand side here, which is one pseudocode, for instance, you can come very quickly to solutions, even if the amount of text is very large. Of course, here, Practical Lecture 5.1 is a much better example of this, but I also provided you a textual representation of this. Again, think about some type of a text stream that comes in like foo, car, bar. You cut it into different pieces depending on how many workers you really have. And then you just simply count 1, 1, 1. You see, it's computationally not really intensive. It's not physical laws, numerical methods. Here we just have very simple computing, just adding a 1 to a vector in the occurrence of a word. And you actually can crush this really small so that, of course, you have more workers and do this nicely parallel and by this accelerated. Now, this is the map phase. Now, what I said to you is before we enter the reduce phase, there's a sort, shuffle, group. The interesting approach that once you do this with the Hadoop framework or with MapReduce, depending on your key value structure, which is here for us, of course, key is a word, right? And then we have basically the occurrences. We can do some, aggregation of the values in the reduce phase. But first, we see the sorting and the shuffling of all the keys. So we have now all the cars, we have all the bars and foos in one, let's say, data structure already sorted, so that the reduce has a very easy step of just counting all the occurrences. This is a visual representation of, let's say, now the really most simplest MapReduce application which still has actually practical significance in the world. So it's actually much more than just a hello world. We already covered a little bit Yarn, so here we come back to this a little bit, that of course Spark is using Yarn, which is shipped with Hadoop. And with this, of course, Hadoop becomes directly important for Spark, interestingly enough. And we see that there's actually more logic behind it. It's not just MapReduce. We have to talk about data nodes, node managers. We will talk in the second part of it. So I just want to give you a little bit of an appetizer that, of course, it sounds so simple now with word count, but underneath, of course, there's lots of smart ideas to make it fault tolerant, to make it dependable, that we will address again in the second part of the lecture. Now, when we think about it, one concrete application example before we, let's say, close the first part of the lecture, let us just look at Facebook. This will be coming in lecture 11 much more about graph databases. I mean, everybody of you knows Facebook, lots of different users, 1 billion new posts per day. So big data problem per se. And they use actually Hadoop for MapReduce jobs and for a very specific purpose. If it's about a search index, which has all these posts, so which is quite some data, and the data that you see there might be even more today. They use this with a specific ecosystem part called Apache HBase. We will talk later about it, a SQL NoSQL database, where we basically then see that they have different databases, different approaches for different aspects in the Facebook realm. And of course, they also use Hadoop and the MapReduce jobs actually to go ahead. But this is something what we will have in lecture 11 much more in detail. I couldn't cover everything, but it shows you that MapReduce has real impact. And you see there also HDFS, which we'll address in the second part of the lecture. So here's a video for you again, summarizing all of this, in my opinion, quite nicely. You have different mappers, different reduce, and also application examples. So I encourage you to look at it, also because it fits in nicely with the lecture 2 with the HDFS blocks.